So real quick as a review, I'd like you to go through these two examples, finding component form, and these two examples, finding the magnitude on your own using your formula sheet. See what you remember from last class. So component form on the first two, you subtract the terminal point minus the initial point to get your component form. The magnitude, I found component form first and then did square root of x squared plus y squared on both of them. Any major issues with those two types of problems? I know it's been like a week and we did a test in between, so there's that. If you've got those, flip to the back page. We're going to do the same thing with the first two examples on the top, and then we'll jump quickly into the new material. So the first two examples on the back as well should be reviewed to us. They give you the vectors. These are just doing vector operations. So these two right here. While I'm putting up answers to the second one here, you see the answer to the first. The second one, it's stupid. It's little multiplication and subtraction, but with the double negatives, it can get a little bit funky. One way that I've seen people do that, you can either distribute the 2 and then subtract, or you can distribute the -2 and turn it into a plus problem. I actually find that a little bit easier as long as you remember that when you distribute the -2 in, it turns this into a plus here. So now that's 2 and 8. You get the same answer either way. But some of you, it will help with the minus and negatives to make sure you get the right way. Any issues with review problems? All right, real quick. First new topic, unit vectors. It is a vector that has a magnitude of 1. Really, at this current point in time, they have zero purpose. I'm just going to be bluntly honest on that. They do have a purpose in calculus. If you're going to continue on to that, they do have a purpose in physics. For right now, the reason I go through this is because the dual credit exam asks you to find a unit vector. And it's not hard, but you just have to know how to do it. So the formula for a unit vector, and this is on your formula sheet too, you find a unit vector by taking both components, the x and the y, and dividing by the magnitude. That is it. So how that looks, if they ask me to find a unit vector for this, the first thing I'm going to do is find the magnitude v. So the magnitude is the square root of 4 squared plus 2 squared. This gives me the square root of 20, which reduces to 2 root 5. So something we already know how to find. To find the unit vector, it is a vector as an answer. You take the original vector and divide both parts by the magnitude. So in each component, what's going to happen with the top and the bottom here? Something's going to cancel or simplify. So the first one, it reduces to 2 over root 5. The second one, it reduces to -1 over root 5. This is one where we'll just practice fixing the square roots because in the dual credit stuff, it would have a proper answer to this. So how do you rationalize the denominator on that? Or fix it? Multiply by root 5 top and bottom. So my final answer for this would be 2 root 5 over 5 for the x. And you can write it as -1 root 5, but I would just have negative root 5 over 5 here. If you did plug this new vector into the magnitude formula, the point of the unit vector is it does work out specifically to a magnitude of 1. Okay? So that would work every time. Let's try this for a second one. They give me the vector w. First thing I find is the magnitude of w, and simplify it if I can. Square root of 25 plus 9, or square root of 34. In this case, does not simplify. To find the unit vector, we just take each the x and the y component and put them over the magnitude. Can either of those simplify? No, so you just multiply by root 34, top and bottom. So 5 root 34 over 34. -3 root 34 over 34. These are both vectors with magnitude 1. It's essentially it for that. Any difficulty on that? Yep.
I have a question on the four.
Yep.
So once you simplify 4 over 2 root 5,
Mm-hmm.
the negative 2 over 2 root 5, did you just put like you combined them and just put them over 5?
I just multiplied each of these by root 5 over root 5 so that I could fix the square root on the bottom on both of them. Yep. That's where I got that. Real quick, flip to the back of the packet, the very back page, and try the same thing with 8 and 9. All right, at the bottom of that page, after the discussion of unit vectors, there's this whole long paragraph here. This is supposedly the application of unit vectors to vector notation. None of that actually makes that much sense. So here's the gist of this entire paragraph. There are 2 ways to notate vectors. Up until this point, we've been using this one. That's component form with the x and the y in it. Okay? You can also see this notation for vectors. They mean the same thing. Okay? And the literal difference between them is that the notation is different. Like, that is the only difference. So what I mean by that is, and this is on the top of the next page, on the top of the next page, if you have a normal vector problem here. We just did one like this. They've given me initial point and terminal point, are these 2. I would go through finding component form just like I normally would with 2 minus negative 3 and 6 minus negative 3. Component form, which we're getting used to, is 5 and 9. You could also write that vector by putting the 5 in front of the letter I and the 9 in front of the letter J, and that is just a different way to write it. The X goes in front of the I, the Y goes in front of the J. That is the difference. The main reason we talk about it is because if you look at the bottom right example on this page, they can give you a vector in that form, and you just need to be able to pull the information out from that notation. That's the only reason. So the same thing in the example next to it. If you would take a minute and just do exactly what I just did on that example next to it here. All right, so that's the second example there. And if you need a reminder of that, that is on your formula sheet here. It does say linear combination of vectors. So if you forget that on like a test or a quiz, it has the actual phrase there, linear combination of vectors. It just has the X in front of the I, the Y in front of the J. That's it. Okay? All right, the last 2 things we're talking about here are magnitude and direction. That's a second way of giving you information about a vector. So in this middle example here, they give me the magnitude and the direction of a vector rather than giving me the x and the y. And then they're asking you to find the x and the y. This is a combination of use of your calculator type stuff and your chart, which I have written up on the board here, the sine, cosine, tangent chart. There's 2 ways to go about these kind of questions. One is to memorize another formula, and the other is just to draw it out and understand how to find it using right triangles. I prefer the understanding version because that applies to the last 4 examples that we're doing, and I don't like to memorize a ton of formulas. So that's just kind of how I feel about it. So what you see here in this box is the picture of the vector. They've said, here's the 60-degree angle, so just like the unit circle, from 0 up to 60 degrees, they've drawn a vector out that is 7 units long, because that's the magnitude. So to find component form for this, all I do is draw in the x and the y side, which makes your triangle. Component form is literally the x, which is the bottom side of the triangle, and the y, which is the side. All I have to use in this then is sine, cosine, tangent to figure this out, right? So if I wanted to find the x component from that 60-degree angle, is that the opposite, adjacent, or hypotenuse? It's the adjacent. So what should I use, sine, cosine, or tangent? Cosine. So I'm going to go ahead and set up cosine of 60 degrees is equal to the adjacent over the hypotenuse. How do I solve that for x? Okay, I multiply the 7 over here. Now, if you are using an angle that is in your chart or able to be figured out using your chart, we're going to do exact answers without a calculator. Okay, and here's how this works. That's 7 times the cosine of 60. Well, how do I know what the cosine of 60 is? Well, I think about my chart. 60 degrees, the cosine's what? 1/2. I plug that in. What's 7 times 1/2? Okay, 3.5. I can do that, or I can do 7 over 2. I'm going to do the same thing to find the y component. Only in my little triangle picture down here, the y component is the opposite, adjacent, or hypotenuse. Opposite. So I'm going to use what instead? Sine. Sine of 60 degrees is equal to opposite over hypotenuse. Just like before, I multiply the 7 over here. This time, where do I get the sine of 60? Go to 60, go to your chart. This is the one that really matters about not using your calculator, because if you ask your calculator to do this, since it's a square root, it's going to give you a nasty decimal. Where here, we're going to keep our y component as 7 root 3 over 2. So my final answer for this question, I can do 3.5 for x, or I can do 7 over 2. And I can do 7 root 3 over 2. I feel like if you understand where to draw it, it really kind of just helps you with the whole understanding what you're actually doing. So we're going to do the same thing for the second one here. This time you have a magnitude of 12 and a direction angle of 300. We have to draw our own picture this time. Where's 300? Okay, it's in the fourth quadrant. They're all here, sorry. All right, there's about 300 degrees. However, I don't actually care that much about the 300 because that doesn't help me where? In your chart. We care about the reference angle. What is the reference angle for this one? 60. Then I can draw in my x component and my y component and set up solving for that. So just like before, x is the adjacent side, so I'm going to use what? Okay, I'm going to use cosine of 60 is equal to x over this time 12. When I multiply the 12 over and plug in the 1/2 for the cosine of 60, what do I get for my x component? 6. The only thing that I have to consider that we didn't have to consider in the first one is positives and negatives. Okay, what quadrant are we in? Fourth. In the fourth quadrant, should the x's be positive or negative? Positive. The y's, however, should be negative. So when I go through and I use sine of 60 to find the y, from the last one we know sine of 60 is root 3 over 2. If I simplify that, it's going to give me 6 root 3 for the y. However, in my answer, because I'm in the fourth quadrant, I'm going to make it 6 and negative 6 root 3.
So this would only be a non-calculator if you give us one of those reference angles.
Right. If I give you something that's not one of those reference angles, then it would have to be on a calculator section. Okay. Does it make sense why we made the y negative? Okay. Real quick again on the back before we do the last two. Try the same thing with 14 and 15, but take a look at 14 and 15. Are either of those nice reference angles? No. So you may use your calculator just to plug those in. I do want to talk about 15. How many of you used 132 as your angle? Because you can. How many of you used 48 as your angle, the reference angle? If you use the 132, since you're plugging it into your calculator, it will actually give you the exact right x and y, including positives and negatives. If you use the 48, the only issue is you have to think about the negatives. I actually don't mind that because I prefer you know which quadrant. It's a good number sense thing to know which quadrant has a positive x and a negative y or so on. So either way you did it is totally fine, and you can get the answers right. In 15, since you're in the second quadrant, what should be negative, the x or the y? The x should be negative, right? So in that one, if I did it that way, I would use 8 times the cosine of 48, but I would make it negative 5.35. The y, 8 times the sine of 48, which gives me 5.95. Okay. Any issues with that? All right, we are going to finish up with the last 2 questions then, which are example 7s at the bottom. This is very similar to what you're doing to find a direction angle. If they give you a component form and ask you to find direction angle, I prefer to just draw it out. Again, because you do need a calculator for this one, it's good to know what you're looking at and where the angle actually is before you just trust your calculator blindly for the answer. And we're going to see that on part B over here. So the first thing I would do in this example is draw out where the vector is. If the vector is 2, 9, where is it going to be? Quadrant 1. Right 2, up 9. There's my vector. Okay? What angle am I looking for there? The bottom left. Right there. Now, from that angle, what 2 sides do you have? Opposite and adjacent, which means I'm going to use what? Tangent. So I set up tangent of the angle is opposite over adjacent, and how do I solve for the angle? Okay, I use inverse. Now, remember, tangent is positive in the first and the third quadrant and negative in the second and the fourth. So the calculator may not always give you the right answer. Please use judgment when it spits your answer out, and this is why I draw the picture. Okay, does 77 degrees make sense for where we're at? Yes, it does. Now, let's try the same thing in the second one. First off, notice the notation here. This is not supposed to scare us. We're just supposed to be able to know that's the same thing as component form, right? Just pull out the x and the y. Again, if I drew it first, which quadrant is this one going to be in? Second. Negative 7 up to, here's my vector this time. Okay, if we set up, we're still going to find that angle, the reference angle, right? Excuse me. Now, just like before, I'm going to set up tangent of theta is equal to opposite over adjacent. When we do inverse tangent here, inverse tangent of 2 over negative 7. What do we get back out? A negative angle. Okay, let's review. I get out theta is negative 16. This is the problem with trusting my calculator just blindly to give me the right answer. Where is negative 16 degrees? Over here. Now, why does my calculator give me that? Well, because tangent's negative in both the second and the fourth quadrant. Okay, that doesn't stop me from finding the answer. This is still a 16-degree reference angle. However, the direction angle is the one that I want that starts at 0 and goes to where the vector is. This is the... Okay, I find that angle, my direction angle, by doing 180 minus 16. So see what I mean about not just blindly trusting our calculator? Doesn't always give me the right answer back out. It can help me. Okay, it gives me the reference angle, but it doesn't always give me the exact right answer. Okay? Now, I have another page that's going to be your homework. On the back of this packet, we are going to finish what you haven't finished, 8 through 15. Okay, so the back of this packet, you're doing 8 through 15, what you haven't done. And then the other page is more of a full review for your quiz. So it has some of the stuff from last class.